Okay.
Okay. So welcome to HAO colloquium today. It is a special colloquium. Our speaker is Vladimir Erapetian. Um, um, Vladimir Erapetian is professor at American University, Washington, D.C., senior scientist at HSD-GSFC, and distinguished professor at Kyoto University, Japan. He received his BSc MSc in theoretical physics from Yerevan State University and PhD in theoretical astrophysics under Professor Ambar Sungyan at Burakan Observatory in Armenia. Since 1994, Vladimir held a postdoc position at Los Alamos National Laboratory and NSO Sunspot, and he 1 year later joined NASA GSFC as AST/HST support scientist. In 2010, he is affiliated with HST to complement his stellar research with Sun as a Star Studies. Since 2015, Vladimir Erapetian is one of the founding members of Sailor's Exoplanetary Environments Collaboration um, at GSFC, a member of NASA's steering committee of NXS and prebiotic chemistry and early earth environments networks. Vladimir Erapetian is currently leading and actively participating in 4 complex factors supporting the origin, evolution, distribution, four complex international interdisciplinary research projects. These projects aim to understand the astrophysical factors supporting the origin, evolution, distribution, and future of life in the universe. The International Multi-Observatory Observing Campaign, Evolving Magnetic Lives of Young Suns, including HST-COS, New Star, TESS, NICER, complemented with 2 radio facilities, MWA, ATCA, and Anglo-Australian ground-based telescope. Project to develop and apply a sophisticated tool, Planet ITTR, to model atmospheric escape from rocky and giant planets, funded by SEEC. 3. MHD modeling of corona, winds, superflares, and CMEs from young solar-like planet hosts, and to study the impact of prebiotic chemistry and climates of rocky exoplanets, funded by SEEC, NASA Exobiology, XRP, NICER, TESS, HST, and HST XMM Newton programs. 4. Laboratory experiments of proton irradiation of gas mixtures resembling the current early Earth, Mars, Venus, and exoplanetary atmospheres at Tokyo Tech, YNU, Japan, NASA GSFC, and American University EPIC Lab at GSFC. So today, Vladimir Erapetian will be talking on space physics of habitability, system science approach.
Thank you very much for your introduction. And yeah, I'm really, thanks for inviting me to HAO. So the second actual visit. I've been here many years ago, 7-8 years ago. And yeah, just briefly talking in one sentence, I am a theoretical astrophysicist who evolved into the heliophysicist and later evolved in astrobiology. So basically, working on connecting the dots between heliophysics, to astrophysics, and to planetary science, to understand the complex questions of habitability. And so I'm talking, on a really spooky day of Halloween. Yeah, without a costume, but the building can be spooky. And I'll talk about some of the, spooky aspects of the habitability using the system science approach. And so you can see on the, the corner, a team of superheroes that are part of the collaborative team. So one of the superheroes, so it's here present. So yeah, and so in order to understand this, it takes a village, to understand this complex questions. So, and I will try today to give some kind of overview of the, how we approach a problem, what tools we use, what kind of results we have in a general way. So the big question that we're gonna, address is are we alone? It's a real ambitious question that we've asked, for thousands of years, and now with the advent of science missions, and with the advent of really understanding of the, this integral relationship between Earth and the Sun, and understanding the solar processes better and the universe better, we can address this question, from a scientific point of view. And specifically, one question that I will discuss is Earth a unique planet? What makes Earth unique, or maybe common, common joint street, or how can we reconstruct space weather from young solar analogs, to better understand whether our sun is a common planet, common star, or it is a unique star. And then, we'll discuss the transient events from young solar analogs and how they impact magnetospheres and the lower atmospheres of rocky exoplanets using the one recent event from the sun that, with the known benchmarks as a proxy for the impacts of those super flares on exoplanets. And eventually we'll talk about the chemical signatures of prebiotic planets in the era of JWST, not only from the theoretical point of view, but also, through laboratory experiments. Okay, so first I want to start with this, the whole topic, of course, started back in 1995, when, the first extrasolar planet was discovered using radial velocity method, and then with the advent of the Kepler space mission that had the 150,000 stars observed simultaneously over the course of at least 4 years. And imagine that if you're looking constantly, staring and in pixel by pixel, and so many stars, so you reveal such a great diversity of exoplanets. We found the planets like the Earth, all the way to Jupiter, even larger than that. You can see they're all pretty compact, and that's of course observational selection. If you consider the solar system, which much bigger, that spans to tens of astronomical units. Here we're talking about only a fraction of astronomical units. And of course, this is now we have information about over 5,500 exoplanets and counting. Practically every day, people report detection of exoplanets. Now we have TESS, Trans-Exoplanet satellite, and the survey satellite, and now with the advent of James Webb Space Telescope, we have for the first time really unique opportunity to not only to detect planets but also to characterize their atmospheres. So if you look at the the whole picture, so that's the plot that shows the planet radius, detected radii of planets, and you can see that how many different methods are used. I'm not going to concentrate on them. Mostly it's radial velocity, and which allows us to measure masses of planets, and the transients that gives you the sizes of planets. So that's how we know the density. So we can discriminate between the rocky planets from giant planets, and you can see that. If the horizontal axis presents the orbital periods in days, the vertical axis gives us the information on planet radii in the Earth radius, and you see one that's the approximate how many planets we already detected, like this. Okay, so and you can see that our Earth stands a little bit far away, at the orbiting our sun on 365 days, and you can see that most of these planets that we found so far are, it's like exoplanets are pretty close ones with the orbital periods, with the, believe it or not, less than a day, all the way to a few tens of days. So which suggests that and that this is basically pretty close-in environments. And you can see that the Neptunes and the Jupiters are also very well represented. But you also can see something in between Earth and Neptune, some kind of planet that we never encountered in our solar system, so called super Earth. The planets that are larger than Earth, that are not present here, but they're very numerous and very populous in the whole demographics of exoplanets. So, and then on the left-hand side, you can see some kind of this, you can see the basically a relative absence of the planets that, so-called Golden Gap that we also would understand. So this allows us to, to apply tools that we normally use in solar physics, in heliophysics, to understand what's going on, why we see what we see. Because if you go further away, of course, here some of them are observational selection, but when you go close-in planets, we definitely should see some kind of some hints on physical evolution of atmospheric environments of those planets. So,
Okay, to ask a question?
Sure.
Okay, so that plot that you showed earlier, I mean, the star type should matter too to the habitability. So should that be like a three-dimensional plot with a third axis star type
Yes,
to put something in the same part of the parameter space as the Earth?
Yes, definitely. But so because the 77% of all stars that in our galaxy are stars like M dwarfs, which are much cooler than our sun, with the average temperature between 3,500 to 4,000 kelvins. Yeah, the cooler M dwarfs, and so basically they are most populous planet-hosting stars. Of course, some of them are K, slightly cooler, and they G. So, and they're gonna concentrate on those kind of stars. But here I just give the whole, a plot of exoplanetary environments. But yes, of course, the third dimension also matter, and with the only 10% of planets like the sun in our galaxy.
Yep.
Okay. Yeah. So those environments, and now you can see the plot for the stellar types. That's the question that you asked. So that presents the case to move from heliosphere to astrospheres, to understand the astroperic environments of those exoplanets, because we have good information now. You can see from F0 stars, which are hotter than our sun, all the way to M9, which are extremely cold environments, but like 3,000 kelvins. So, and you can see that all those stars, the one unifying property is their X-ray and extreme UV emission. Okay, so this is the factor that is very important for space weather, right? For Earth and other planets. And you can see that extreme UV luminosity for those stars, vary and of course depends on the age. The younger the star, the greater the flux is generated by the transition region and coronal layers of stars. So we go from 10 to the 32, a few times 10 to the 32 Earths per second, all the way to but the regular solar, like 10 to the 26 Earths per second. So that spans 6 orders of magnitude. And given that those planets that I showed in the previous plot, that they're pretty close, you would imagine that how much flux is received at the top of the atmospheres of those exoplanets that basically shape and sculpts the atmospheric escape, atmospheric environments. So, for instance, here is the XUV flux, for instance, goes like 84 times watts per square meter, and the tau is the age. Okay, so it goes from the XUV fluxes. XUV means the X-ray and extreme UV. Okay, basically it's from 0.1 to 100 nanometers to Lyman alpha. So so the fluxes vary for solar type stuff, pure magnitude, at 1 AU, let's say. So therefore, the question is to understand those environments. You can see that one reconstruction of the fluxes. So we're interested not only in the black body emission, but also the ionizing fluxes. And you can see that the Earth versus, let's say, Proxima b. Proxima b is the closest exoplanetary system to us that can be studied pretty well. And you can see that the flux received by Proxima b planet, which is the Earth-like planet, is 3 orders of magnitude greater than we receive at Earth. And every time that we have magnetic storms here, we try to be very careful and sometimes, complain, like, character type event. But imagine the environments there. So therefore, the whole goal is to study those extreme environments. So I know to understand the extreme environments, the TRAPPIST-1 probably one of the best, representative cases of, a dwarf star and 7 dwarf planets. I would imagine that they're good representative for Halloween, to have this one cool dwarf and mother 7 planets, pretty small, and you see that they're orbiting within all within the orbit of Mercury. Okay, so the closest one at the distance of 1/100th of AU, so the furthest one at the distance of 0.16. Imagine the scale of the whole system. And currently, James Webb Space Telescope is trying to find signatures of exoplanetary atmospheres. And so our goal is to come up with the predictive models to basically understand what planets can have atmospheres, which don't. So because the space weather can affect the so-called habitable zones, and which is basically the zone, the region around the star where the flux, total bolometric flux received from the planet creates the average temperature, surface temperature on the planet between 0 and 100 degrees Celsius. So it's not too cold, not too hot. It's kind of Goldilocks zone. But that's one parameter that is used in exoplanetary science. But by itself, the habitable zone is evolving factor. It's a dynamic factor because it depends on the age of the planet. So the first question we want to understand, is Earth a unique planet? Or is that the right question to ask? Is the Earth a unique planet? Because some people are looking for Earth 2.0, and for Earth 2. Or we need to ask the question, is the Earth Sun is a unique system? So should we look at this as a planet, or we need to look at the system? So, and the question is that more and more we study it, we understand that, it's Earth Sun. It makes sense to ask the question, is the Earth Sun is a unique system? And what is this interaction, how this interaction evolved over the last 4.5 billion years? And whether the current environment, that we observe, can be used as a proxy for finding, signatures of life in our galaxy. So, in order to understand it, I don't understand why I didn't see the one upper. Oh yeah, right. I do see it now. So, the one big question that we want to ask is how habitability state. So it's not habitability zone. it's a modern habitability state because the environments varied, evolved in the solar system. As you can see, our sun, at ages less than 300 million years ago, not the million years old, sorry, not ago. You can see that our sun was highly dynamic, spotty object, and as the star ages, of course, its rotation rates, so that it becomes lower, so it spins down. So the alpha mega dynamo becomes less and less efficient, generating less magnetic field, and as a result, less and less, magnetically driven transient events, including flares and coronal mass ejections. So that's where our sun, almost spotless, boring sun. But the question is that this star is boring? Can our sun show signatures of a star like, this one, let's say, active star? So that's one question that is very legitimate and needs to be investigated. So as a result of it, as you can see here, the lower plot, so that's the how, the trajectories, evolutionary trajectories of planets from Mercury, Venus, Earth, and Mars, and green is the habitable zone, okay? That's where we enjoy today, right? But it was pretty tedious, trajectory to move first from the, hot Earth, driven by the accretion processes, and then representing like a magma ocean, eventually cool down at that level, okay? And that happened in the first, like 10 million to 50 million years. And at that point, the primary atmosphere got escaped, but that was the most critical moment for the secondary atmosphere that we enjoy today, which is driven mostly volcanic activity. So, and as I was driving from, I took Uber from Golden, looking at those beautiful mountains, which is, reminds me that we need to thank those mountains, for being here on Earth, because this atmosphere, the secondary atmosphere, is a result of the volcanic and tectonic activity. So therefore, one important point to keep in mind that the tectonic activity, geophysics, is very important for habitability. So, and then of course, once you have this atmosphere, which is nitrogen-rich atmosphere, so that's another question to ask. Why do we have like 77% of nitrogen? Is that again coincidence, or there is some kind of a common physical process that drives this? Looks like that the N2 CO2 atmosphere is the result of the tectonic activity and volcanic activity, as we understand today from geophysical models. And then, as you can see that the Venus was there. And then, currently, as the sun becomes older, its volumetric luminosity increases by 10% every billion years. So eventually, we are going to be out of the habitable zone, and so that's the Earth. At some point, I'm talking about like in 1 billion years. In 1 billion years. We're gonna start, seeing this global greenhouse effect with boiling oceans, and eventually, moving into the Venus zone, into this red zone. Okay, so therefore, habitability of our planet is also pretty tension. Another parameter that actually affects the habitability is magnetic field. As a magnetic field is a result of the, of liquid outer core, that also by itself undergoes the secular cooling. And at some point, that's our recent models show that in 600 million years, the Earth will lose magnetic, because the magnetic dynamo number becomes small enough to allow efficient regeneration of the field. So the magnetic moment will be dropped by 5% of today's magnetic moment. So you can see that the same happened to Mars. So and that's in a cold zone, but it will get into the habitable zone later on. Okay, as we're gonna be out, the Mars will be in. So therefore, it's very interesting trajectories of the habitable state. So that's why we probably need to talk about habitable phases, transition phases, rather than the habitable zones. So, and that's another thing that if we think about the Earth, whether it's a unique planet or not, we can look at the geological records and find that, depending on the different phases in the Earth's history, and that's starting from 4 billion years ago all the way to zero today, as you can see that the amount of oxygen, very dramatically from basically no oxygen at all. Okay, it's less than 10 to the minus 4, and all the way to this is the one. It's normalized by the carbon. Which, by the way, 21% of oxygen that some astrobiologists are looking for are pretty much overkill, because just over the last 500 million years since the Cambrian explosion, for instance, the amount that we have the data that tell us that the oxygen amount varied between 5% and 21%. And in order for cells to function properly, you need like about 5%, a few percent. You don't need 21%. We're survivors on this planet to basically deal with the oxidation. And so therefore, that gives us a pretty good idea what we should look for. I mean, is that too much oxygen good? It's not. So another one is the methane. So see that the first, the first 1.5 to 2 billion years of the evolution of our planet was a pretty boring place, filled with methanogens. Increasing the amount of methane to like 1,000 parts per million. Today it's about 1.8 parts per billion, around 3 orders of magnitude. And now it's of course very, very low amount. So that gives you a good preview, what's going on with our planet. And if we're looking at the planet, what kind of Earth-like trajectory we're gonna catch, from that planet? So therefore you can see that this is a very complex question about what kind of transition are we talking about in the history of a rocky planet versus what the star is doing, okay, depending on its spectral class and depending on its age. And of course, the planet and star co-evolve together. So, yes.
So in that transition, that looks like a step function. How wide or how long is that step function?
It's an excellent question. So this is the beginning of oxidation, beginning of this oxygenation of our atmosphere. This is the beginning of the when biology invented photosynthesis that we enjoy today. That the photosynthetic process was absorbing carbon dioxide and releasing oxygen into the atmosphere. And it took some time, but it might be a few tens of millions of years. But in order to first oxidate the rocks, then oceans, everything that you can oxidate, and then all the environments on our planet, and then start to form the free oxygen that can be released into the atmosphere. Okay, that's what happened. And then this process was actually this question. I didn't talk about this question. You see that this is basically some of the trajectories, some variations into the ice ages and hot earths, so that we go from time to time. It's over the last again a few 100 million years. Earth has undergone through not only changes in oxygen, but also carbon dioxide, okay, and the temperature. So really hot periods.
Is this a reason the sun is fluctuating?
Yes, it is fluctuating, and we don't know how long it will fluctuate, but it's always fluctuating because of the so-called carbon cycle that basically is so important for the habitability, for regulating our planet. So now I'm moving to the strategy that I take. It's to study the evolution of the star-planet system, in space weather, in order to filter out uninhabitable worlds. Something that, we can do today once we understand geophysics, more or less. We can study this intricate relationship between the star with the, especially early on, because we know that life on Earth started pretty early, and in the first, probably in the first 100 million years. So the more and more we go in the prevailing chemistry, the more and more we realize that it probably started as soon as the conditions became available, the all basic conditions that they can talk about that later on. But we know from data that those kind of young stars are really, very active, showing flares, mass ejections, and energy particles that penetrate the atmosphere. Of course, this is the magnetized planet, and so the particles penetrate in and create, showers that, depending on the energy, can reach the lower atmosphere. So the question is that, how those energetic events could affect the climate of the planet, and if we can learn about the climate, what kind of signatures we can produce from that. So, to understand that, we can reconstruct the other stars using the first empirical method, studying the so-called sun as a star approach, by looking at the scaling laws between the radiances, of the emission lines formed from the chromosphere, transition region, and corona, and total unsigned magnetic flux. And that's what we did in a series of papers by looking at using the STSW data, using the EVE data, using Hinori data, GOES data, or everything that we had over the last 11 years. To study how the total magnetic flux, varies, how the irradiance varies in response throughout the solar cycle. Okay, and you can see here that there is a very high degree correlation with the power law, with the indices varying, for the low temperature line was less than 1 to about the transition region 1, and the coronal lines greater than 1. That shows that it's a strong coupling to the magnetic flux, in the corona rather than in transition region, which informs us about the competition between the wave-driven heating versus the nanoflare-driven heating. So the question was, what will happen if we put some solar-type stars? That's what happens. So because now that we have the great opportunity to measure fluxes, we can basically study whether other stars obey this kind of solar type statistical correlations. And so the next study is to add the M-tours, the most popular part, to understand, whether we can apply. But this shows that we can apply the, methodologies and the heliophysics tools of the tools that describe our sun to solar type stars. But we're not sure about the other stars. So this is the, a portrait, of the young sun, around when the life started on Earth, from Kepler data. So each panel is the 1 year. So it's a 4 years of continuous, continuous data, rather basically rotational modulation. Okay, rotational modulation as traced by star spots. That's what you see. Then the star spots from young stars were much bigger, 10 to 50 times bigger than we observe today from our sun. And on top of it, you see those, so this is the star spots, come and go, and you can see that, they're leave only might be a few months. And on top of it, you see those blue spikes. They're flares, and some of those big guys are super flares. And when I say super flares, I mean that the flares with the energy greater than 10 to 33 ergs. So, which is basically larger by a factor of few of the Carrington. So basically, as you can see, that the flares were pretty frequent, on the young sun. So therefore, the question can be asked whether those flares come with the coronal mass ejections, because from the solar data we know that there is a close association of the coronal mass ejection, with the X-type flares. And because CMEs can directly affect the exoplanetary environments, their atmospheric escape and the chemistry, and can affect habitability, and it also can shed off the angular momentum. So it would be very important to somehow detect those elusive CMEs from other stars, like our sun. Of course, it's easier to do from the stars like our sun in its infancy because of the greater, frequency of super flares. Believe it or not, that the highest one is like one event per day. So therefore, you can apply for observing time with different telescopes and have the great success in detecting them. So basically, that's how the CMEs can affect the magnetospheric environments of exoplanets, cause the atmospheric escape, eventually atmospheric chemistry they can talk today about, and also affect stellar mass evolution and angular momentum evolution. So the one way to detect it, and again, learning from the sun as a star, is to look for the blue shifted Balmer emission, like H alpha emission, and then you can do it from the ground. You don't need any space mission, any space telescopes, right? So the idea is that as you have a prominence eruption or the filament eruption, so you have the signature of H alpha shifted. If the blob comes towards you, and it can be detected depending on whether it's projected on the disk or not, or on the limb. It can be in emission or in absorption. Okay, so that's the one of the cases, the absorption, the filament eruption detected on one of the young stars by Koskin Namigato, our team member, superhero, that basically was the few hundred kilometers per second. So we started this project recently to increase the number of stars with the whole flotilla of space missions, and the second way that we learned again from our sun is that as this huge magnetized flux robe leaves the solar corona, it creates some kind of reduction of density, which basically creates some dimming in X-ray emission for a few hours, and that's known as XCV dimming or X-ray dimming or EUV dimming on the sun. But because the corona are much hotter, that can create XCV dimming. So therefore, there's already a number of cases, already 22 events detected from L and K dwarfs with you can see here, when that was the flare and then following with the reduction of the flux, okay, with respect to the background flux. So this is the region of the dimming, for instance, from Proxima Centauri, one of the closest stars with the next planet, okay, and this is the image from our sun. So that's how, learning from our sun as a star, we can apply those methodologies to search for elusive CMEs. And there's other methods, of course, but I'm not going to concentrate on them. It's not the topic of our major topic of our conversation. So this is basically our recent result, the paper that almost accepted, where we basically observed one of the stars, EK Draconis, which is only 100 million years old, and we found the signatures of the blue shift emission together with the X-ray dimming. See here, X-ray dimming, and this is the H alpha, emission blue shifts going like 700 gallons per second all the way down. So, which represents the first case of the prominence eruption from solar type stars. So once we have that, we can apply those constraints to study theoretically to basically model the stellar CMEs from young solar analogs. So first we started with basically trying to explain X-ray corona of one of the young solar analogs, Capricorn City, and then once we basically found that we can explain X-ray emission with the inclusion of bipolar regions and 3% sunspots, okay, that can basically match the X-ray observations of the star. We can also, we insert the flux code system, and this is the, the cooler region, like a filament, and then let it go using the three-dimensional Austin code to basically simulate the coronal mass ejection from the star at about 5,000 kilometers per second. Okay, so with the super flare, which is 10 to 34 ergs. Okay, so this is unpublished, but this is the first attempt to use the first realistic background environment and then trace the first shock and then go all the way to 1 AU. This is all the way from 1 AU by 1 AU. So from zero, the sun is at the center, star at the center, and we're looking from north down. So that's the XY equatorial plane. Okay, so next one. This is very important for the atmospheric escape because atmospheric escape is driven by XUV emission from the star and also driven by it changes the the magnetospheric environments, increasing the cross sections. As you can see here, that's what the CMEs do as they interact with the the dayside magnetosphere, especially with so-called the BZ southward. The reconnection and dynamic pressure creates the opens up the polar cap, allowing the particles to basically escape so study applying the model that is used for our planet, we can find the mass loss rate associated with so-called ion escape, and so which are roughly proportional to the incoming magnetic flux. So then there's those CMEs propagate out, so they create shock waves, and the shock waves are very efficient in accelerating particles using Fermi-1 acceleration process. So we have basically we couple the two codes, the MHD code to the kinetic code, so-called IPAT code, to calculate the acceleration of particles in those strong shocks, CME-driven shocks. So why it's important? Because now I'm trying to move to the best proxy we have. It's called solar super flares. The one according to 775 AD, and was discovered by Miyake Group in Japan. That's Nature papers 2012. So when they found that enhancement in using the tritiums, enhancement in the carbon-14, okay, by 15% compared to the background. And normally what happens then when you have a cosmic rays, energetic particles penetrating, they can be mostly, of course, it's the high energy galactic cosmic rays. They penetrate the atmosphere and they collide with those atmospheric species, as you can see here, and they can create products. Although they can create beryllium-10, they create chlorine-36, and they can create as a product carbon-14. It's a radiocarbon, okay? And the carbon-14 is unstable, has the decay time of 5,730 years. So by using this, we can study the and get the good idea about the fluences of particles. Okay, so using these methodologies, so this beryllium-10 and chlorine-36 can be found in ice cores. Let's say in Antarctica. A carbon-14 can be studied by using the old trees, and so that's what people have done recently since 2012. We had a dramatic progress in this area. So what you see here, it's the tree rings. After that 2012 paper by Miyake, you can see that Yamal, in Siberia, latitude of 70 degrees. Japan is 35 degrees. Okay, and you see that those tree rings, the enhancements of the carbon-14 specifically, of the radiocarbon was found, in different places. So, and this blue circle is the 774 the event, occurred 1,300 years ago, 27 sites, across the planet, versus 993 event, it's 8 sites. Since that time, now we have 9 events. So far we knew that 774, 775 event, because the resolution is only 1 year, studying the 3 weeks, is the probably the most energetic superflare known, with the energy about 10 to 34 ergs, okay, from the relatively current sun, right? So just about 2 weeks ago, a paper was published by French using the fossil-like trees, and they found that event 14,350 years ago, which is even twice more powerful than this one. So that means that, our sun shows those superflares, at the rate of maybe 1,000, 2,000, every 1,000, 2,000 years. And Newton also did his study using the Kepler data, found that actually he was looking at boring stars like our sun, with the rotation rate of about 25 to 27, 30 days, and he found that, wow, the superflares are observed. So it happens when you have a good statistical sample, you can find those rare events, which means that, using this data, combining with the astronomical data, we come to the conclusion that those events will happen. So therefore, we want to know. So we want to know what's going to happen to us with the extreme event. Second, we want to know what happened to exoplanets that are experiencing those processes, pretty frequently. So this is this plot shows now we have 9 events, as I said, since 2012, 9 events spanning this period of like 8,000 years in Earth's history. So and you can see that here the blue one is the strongest one, 775 CE. So the horizontal axis is the energy in giga electron volts versus the fluences in 10⁻². So you can see that those events are really hard energy spectra, meaning that and the particles with the energy about a few hundred megaelectron volts to 1 gigaelectron volts can penetrate down to the low atmosphere and can create interesting chemistry. So that's what we did. We studied that how the energy spectra vary in response to the CME speed from 3 different types of stars: the current sun, the young sun, and the infant sun. Infant means that 100 million year olds. This is the 500 million, and that's the current one. As you can see, that not only the fluences get higher, but the spectra becomes harder. And we can find that the maximum energy of protons that can be accelerated, it's about up to 40 gigaelectron volts. So we want to do studies of the lunar south pole, to find the signatures of those dramatic events. So
Can I ask another question?
Sure.
How do those 2 events that happened relatively recently compare to a Carrington event?
Okay,
And
that's a very good question.
could you detect a Carrington-like event in 3 rings?
Yeah.
Was it not strong enough?
Carrington event was extremely soft event.
Yeah.
We don't see any signatures. So therefore, and in terms of energy, total biometric energy of the flare and associated CME, Carrington event, even though it was dramatic for us, but the 775 event was the order of magnitude.
Okay.
Stronger.
Yeah, thanks.
One comment. Carrington event, geomagnetic storm is very large. But
Yes.
Particles.
Yes. Geomagnetic storm was,
Particles.
but it's either particles missed, us,
Yeah.
or we don't know, or the shock wasn't that strong in order to.
Yeah.
Because it's a combination of those things. They want to talk about geomagnetic effect. It's not only the shock, it's not only speed, it's not only dynamic pressure, but it's also busy.
Yeah.
Right. So you need to have this perfect storm, to have a geomagnetic storm. That's what we had, but we didn't have enough particles.
Okay.
Yeah.
Thanks.
So basically, that's what you see. The 1 megaelectron volt protons penetrate to the thermosphere, about 90 kilometers. 10 megaelectron volt goes away to 70 kilometers to the mesosphere. 100 megaelectron volts go away of the upper stratosphere. And so the 1 gigaelectron volts almost goes to like about 3 kilometers. So that's basically gives you the picture what these particles can do. So we used this reconstructed, energy flux, and then calculated the ionization profile, caused by these protons as they penetrate in the ionized atmospheric species. So our aeroplanet's course allows us to calculate this ionization profile, that produces this, the cascade of electrons that are very important in dissociating, molecular species, forming this, CO and NO and different simple molecules. So we use this for the vacuum code. Vacuum code is the NCAR code that it's a climate code that is going from the surface to 150 kilometers. So it goes all the way to even higher than the thermosphere, upper thermosphere. That means that we can use the full spectrum and to understand the full picture of what's going on. So it's community code, and so it's pretty has a high horizontal resolution, vertical resolution, but like 145 kilometers. And so we use this in order to understand the impact of the chemistry. So basically, the whole chemistry is that you can imagine they have XUV flux, SCP particles. That's our current Earth atmosphere, N2 O2-rich atmosphere with a little bit of CO2 and HEO, and then you produce those CO, CH, all those free radicals, and then they combine because all those free radicals, ionized species, mostly neutral species, they are highly reactive, forming the NOx's. So NO, NO2, N2O, and OH axis. And they destroy ozone. So the question was, would be this a doomsday or not? So that's what I would expect. That would be something like, and how long it would take for our atmosphere to recover. So basically what you see here, so the horizontal axis is the days. It's, around 500 days. That's it. And the calculation is still going. Okay, so, and you can see here the response. You can see the NTO, red is NTO. You see that the increase of NTO from the pre-flare level all the way to, that level to, orders of magnitude. When we're talking about from few times 10 to minus 9 to 10 to 6, like 3 orders of magnitude at least. And then slow recovery. So, okay, going back and still going there. So it means that it takes longer than a year. The same time you produce NO, so this is the most important molecule. Actually, by the way, it emits at 5.3 microns, and a cooling effect for the thermosphere of the current Earth. And the green one is ozone. You can see that ozone basically was like around 10 to the minus 6, and a few times 10 to the minus 7, drops down to 10 to the minus 8 by 2 orders of magnitude. Okay. And then slowly recovers. So because because the ozone is such an important for the UVB transmission, this is important to know what the effect will be of ozone on the surface UVB emission for life. Okay, so here you see that global mean vertical profiles. This is the temperature. This is NO mixing ratios, and it's for different days. So the day 0 is red, and magenta is day 500. So day 4, let's say it's this one. Okay, then you can see that the dramatic increase in the mixing ratio of NO, NO2, and N2O. And you see that the N2O is very important because the N2O is one of the most efficient greenhouse gases. Its greenhouse power is 300 with respect to carbon dioxide, which suggests that it can have a 300 times greater infrared trapping ability power than carbon dioxide. It's very important for global warming, and the current atmospheric scientists monitoring this gas, which is mostly a result of biological activity today. So here you can see that the impact can be really dramatic, and the average effect on the climate will be about 1 degree Kelvin on the overall within 1 year, okay, the whole planet. So, which is pretty dramatic. And this is dramatic because imagine that, this event is very rare, right? It might be once every, as I said, 1,000, 2,000 years. But we have many examples of those exoplanetary environments when, stars ejects those CMEs and superflares at the level of maybe few weeks. As I said, even might be few days, but to be conservative, few weeks might be months. But if the recovery time takes only more than like a year, so therefore you can have accumulation of N2O, and that's another factor when the the so-called habitability state will move out. So the temperature will increase dramatically, reaching the Venus zone, so the planet becomes uninhabitable, even though it's in a habitable zone with respect to total biometric flux. But the chemistry matters. So that's the end. Yes.
So from the reconstruction, can we tell what time of the year this happened?
This is a good question. So we did it only for the spring,
Oh,
but we will do. We need to do summer and
climate
winter.
difference.
Yeah. So this is kind of an average effect. Yeah, absolutely. The season matters a lot for the dynamics of NOx's. So this is the ambient dose of the altitude at altitude about 12.2 kilometers during that event. That was calculated in one of the recent papers. And they didn't concentrate on climate, but they did this analysis. And you can see in sieverts per hour, so this is the deadly zone. Okay. So for instance, if you're flying an airplane going from Tokyo to New York City, and crossing the polar regions, then of course, you can get even in 1 hour, not about many hours, the flight takes about 12 hours, get the little dose. Okay, so which shows that the red one is the zone in latitudes that creates this really harmful ionizing radiation environments for the planet. But again, that's what probably will happen, to us at some point. But that's what probably is going on for other exoplanets, from around active, young solar type stars. So this is another thing that we did. We looked at how the SCPs affect not the current atmospheric environment, but atmospheric environment on early Earth with what wasn't N2O2, but was N2CO2. Okay. And because N2 is geochemically stable gas, it basically, two atoms bound by 10 electron volts, one of the most stable molecules in nature, along with carbon monoxide. And you need a lot of energy in order to break it up. Once you break it out, break it up, so you can create reactive species that create all this NOx's and interesting chemistry that, by the way, can create interesting molecules. It can create, see that once you have NO and you have CH, as a part of the methane, you can create HCN. And HCN, it's actually one of the very important, gases. It's a precursor of life gas. As soon as you have this poisonous gas and the life starts with the poison, as we now already know, once you have the HCN precipitates down and creates more complex molecules all the way to amino acids. Okay, so and formaldehyde. So this is the one of the studies that we first did in 2016, published in Nature Science, basically forming this picture. But then creating more sophisticated models, and so this is the more sophisticated models that basically couples our atmospheric code with the phytochemical code that calculates pretty accurately the precipitation of molecules to the ground. But this is a laboratory experiment. As soon as the results were published, I was contacted by chemists, the people who study the origin of life, and that's how I got involved about 5 years ago into prebiotic chemistry, and I learned a lot about chemistry and biochemistry. That to connect the dots, we need to do that. And so basically, together with the Kobayashi-san's group from Yokohama National University, we have conducted a series of experiments, not just playing in the dark like chemists normally do, but basically mimicking the SAP events using the proton accelerator, quantum accelerator, where you can specify, what's your energy flux in protons and the duration of it, and how the mixture of N2CO2 will respond. So you see here the blue. The blue is the amount of amino acids, and we produce amino acids out of the basically the gas, N2CO2, methane, and water vapor. And you can see, and the horizontal, it's the methane amount, starting from 0.5% of the methane, in the original methane, all the way to 50%. And then compared to Uri Miller experiment, we probably heard about this experiment of the spark of life, when the Uri and Miller, they put together ammonia and methane, and then put this, the gas discharge, and they create a lot of amino acids. And that was really a big explosion of our understanding and excitation that, wow, we can create amino acids out of nothing, basically. Here, we repeated those experiments, realizing that methane and ammonia weren't that present in the atmosphere. Instead, it was N2CO2 and a little bit of methane. So, and the red one, that's basically our reconstruction of Uri Miller experiment with this kind of gas, volcanic gas. And you can see that, below 15% of methane in the mixture, you don't see any amino acids, okay? And even, while with protons, we see, with 0.5. And so even at 50%, you see the difference, about, 3 orders of magnitude. And the explanation is pretty simple. Is that because, when you have a gas discharge, you mostly produce, a couple of hundreds of kilovolts discharge. You produce the secondary and the tertiary and the whole cascade of electrons that eventually thermalize from few hundred kilovolts all the way to 10 electron volts that is required in order to start dissociative chemistry, as I was talking about, to create those free radicals. While with protons, you go not with the kilovolts, with mega electron volts, so 3 orders of magnitude greater. So therefore, you have those free agents of electrons that can make it happen. So the process is more efficient. So the recent results unpublished will be published soon. That we did these experiments to show what is going to happen to simpler molecules like nitrous oxide. I showed you this theoretical model right here, 775. Yeah, so we were trying to see that, if we can understand the so-called the faint M-self paradox of the young sun, because, we know that the sun was 25% fainter biometrically, and, by definition, if no greenhouse effect is involved, then the Earth should be an icy ball. But it wasn't the case. It was a, pretty nice hospital planet. So therefore, some kind of gas was involved, a greenhouse gas, and nitrous oxide can be one of them, because those experiments show that the formation, from N2 and CO2, the concentration of 1,000 part per million. Okay, so 1 part per thousand, which is actually, was the input for our, again, that's how we, play once we have those experiments of theoretical model, then play in the climate and see that what kind of solution we can get with that kind of nitrous oxide as a starting point. So we use this, Rocky 3D code that was modified chemically for N2CO2 environments and for 0.5 bars, and added, the N2O at 1,000 part per million. Okay, that which is consistent with what we got from the experiment, and see that we got this average temperature, analyzed temperature 5.2 degrees Celsius. So which tells us that, yes, the climate models show that this N2O amount can explain possibly the resolution of the faint M-self paradox. At the same time, these protons can be sources of as I said, HCN or organic molecules. At the same time, keeping the Earth warm, they can create water, which is the great solvent of life. So you need two components to be present. And so, to continue those experiments, just about 3 weeks ago, I learned that my proposal was accepted to build basically a mirror lab at NASA Goddard. I call it EPIC Lab. It's a planetary particle irradiation chemistry lab. So together with the American University, where we have basically the same kind of same kind of a Van de Graaff accelerator that in Japan, and in Japan it's the only lab in the world. So our lab will be the second one. So you imagine that you produce those beams, like about half a centimeter beams of accelerated protons penetrating into the gas chamber, and so it's a blue and red. It's like say N2O2. That we start with something that we know pretty well, right, from our atmosphere. And the point is that maybe you heard about the Starlink when Elon Musk recently released, about 200 satellites, nano satellites, and most of them were lost. And the reason why that our space weather models, even though they're very sophisticated, three-dimensional, has a lot of thermodynamics, they don't have enough chemistry. Specifically, they don't have enough ion chemistry. Even for a simple system, we don't know what would be the production of NO, let's say. That's one of the gases. NO, as I said, a meter of 5.3 at 5.3 microns. And if you produce it a lot, then especially during the big solar events. And the reason why they lost it, because that was during the, a solar flare that with irradiation of the atmosphere that created some kind of a, missing chemistry that was unaccounted for the stratification of the upper atmosphere created, additional drag force, atmospheric drag force. So that's why those experiments are not only important for, the early Earth environments and exoplanets, of course, but also for, the transient events from the current sun. So what's next? Next is basically to study those climate models, and especially those extreme environments, because extreme environments, as we know, create probably the strongest possible conditions. And even the James Webb Space Telescope is pretty most powerful. Today it's not powerful enough to resolve those using the transit depths, as the light passes from the star passes through the atmosphere of the planet. It creates the certain absorptions, and those the absorptions create different gases. You see the N2O, NO. So this is the hypothetical gases, the hypothetical spectrum that we would expect if we're looking at the right target, irradiated by a super flare. Otherwise, if the star is quiet, then the signal is very weak, and we probably need much bigger telescope than we have today. And this is important because now that after James Webb, we're looking for so-called Habitable Worlds Observatory, which is going to be, this one is 6.5 meters. We talk about 15 meters to 20 meters. And that kind of telescope can really be very instrumental to move us forward towards the habitable environment. And I want to end with the one system that I like a lot. It's the, TOI 700D. It's the planet around M-Dwarf. As M-Dwarf is pretty quiet, has the habitable zone is relatively far away at 0.16 AU. Okay, it's only 6 times further away, close in than we are from the sun. So the radiation environment is not that bad. So there is a good opportunity to maybe use this methodology that I discussed today to find the spectral signatures of the planet. This is like early Earth, proxy. So, my conclusion is that the habitable zone, probably it's a pretty simplistic term, but instead the habitable state is the way to characterize exoplanetary system that evolves via star-planet interactions via the space weather. Okay, so it's the effect allometric and the ionizing radiation. So observationally constrained coronal mass ejection models is the pathway to assessment of habitable worlds. Solar superflares is a good proxy for assessment of climates of early Earth and rocky exoplanets. So we can basically use our Earth as a during the extreme events to validate, the climate codes and also predict what kind of signatures we would expect if we look at Earth at a distance, let's say 10 parsecs. And then, the CME initiate the SPs that initiate a chain of reactive chemistry that can produce pre-biosignatures. So I'm talking about the pre-biosignatures are probably easier to find, again, because of the greater rate of sugar flares that can produce N2O, NO2, HCN, formaldehyde. And so the next step in this is to complement the experiments, to complement theoretical models with experimental facility, with EPIC facility that we're going to start, later this year. Thank you very much.
Thank you. Questions? And people online, you can unmute and ask your questions. There are already a lot of questions during the talk. So, and from the hall.
That was very interesting. I'm not an expert in exoplanets, but I have a few questions. So when you in one of your first slides, you showed that graph of planet radius versus orbital period.
Right.
So we kind of know how good are our telescopes at detecting signals.
Right.
So if you kind of look for the prior distribution of that figure, like what do you expect to see? Like we kind of know like what our telescopes can detect and can't detect. So in a way, knowing what we see now, do you expect this graph to be like full everywhere? Like, do you expect?
No. So, for instance, we probably can understand what's going on here. Then why we have a gap? Let's say.
So it's not because of the telescopes.
No. It's not because of the telescope. It's because of physics. Because of physics and chemistry. It's the combination of the lower surface gravity and high XCB flux. That and possibly that's another topic that I haven't mentioned about is the so-called escape, not due to the XCV flux only, but due to the so-called June heating. Because those giant planets, between Neptune and Jupiter, probably all of them have magnetic field. So magnetic field is hard to expect not to have the magnetic field. But imagine that at that point when the planet is so close to the star, the stellar wind basically induces the ionospheric currents. And if the conductance of the upper atmosphere is appropriate enough, then your Joule heating, which is the product of conductance and the current, can create the heating rate, Joule heating, which can be even greater than the heating. Okay, so we can understand this part.
Okay.
We can predict this part. Yeah. So, but of course, here we talk about observational selection. Here we talk about observational selection.
Actually, I have a question on this plot figure too. What can we interpret it as like bigger planets somehow get closer? Because first you have the trend going this way, and then after Neptune, it goes the other way. So can we interpret it as, or it's just maybe a bias from observations?
Well, again, all those planets that are pretty close to, they're not observational selection because it's so easy to find. The radial velocity, that can be measured pretty accurately. So therefore, if the planet is massive enough, so we can detect it by radial velocity, or if it's large enough by transient method. So we see that how many methods have been used for now. And so with the direct imaging, we can go even further out. Okay, that's the next step, by the way. So what I'm saying is that, so such a high density of massive planets close to the star as a result of the migration. Yeah, and the migration also depends, as we know, from density of the circumstellar disk, how much disk is there. So, yeah, and shows basically, the diversity in the planetary formation history.
I had one more question. Yeah, when you showed a lot about the history of O2 concentration and methane concentration, the methane concentration plummeted with life coming to Earth, and methane is unstable. And I always thought that was one of the things that people wanted to see with James Webb, was like looking for methane. So does this mean that actually methane is not a biotracer?
Well, okay, let me go to that plot. It's a good question. So yeah, we're talking about the methane, right? Which drops down, and it drops down as the oxygen goes up.
Mhm.
So the interaction, it's very hard to have the coexistence of oxygen.
Oh, I see.
That's why. Yeah.
And do you include all those chemistry you mentioned at the end in the vacuum simulation, the HDN and all those?
So no, not for now. So the simulations that I've shown, vacuum simulations, is basically a response of the current atmosphere to 775 AT event.
Oh,
And so next step is that what we're working now are basically adjusting the vacuum code. So now we have the vacuum code that the vacuum code that we use here goes from 0 to 150 kilometers off the ground, but now the CCMC, so Community Coordinated Modeling Center at NASA Goddard, has the more updated version of that code that goes all the way to 700 kilometers.
WACOM-X.
WACOM-X, exactly.
Yeah.
So we're going to use the WACOM-X
Right.
because WACOM-X will, I'm calculating the magnetospheric models. That magnetospheric models gives me the outputs that can be directly related without bypassing anything. That will be very realistic representations. We will, after publishing this paper, next will be to produce 775 with the whole code, coupled directly. Yeah, and then of course, in parallel, what we're doing with a couple of postdocs at NASA Goddard, we're basically working on changing the chemistry, removing oxygen, and adding carbon dioxide.
Earlier.
Yeah, that's right. And not only earlier, but it's most representative, exoplanetary rocky atmosphere.
In a different question. There was a discussion during the talk when Carrington was solved. The Yaki event was hard. What physics determined that soft and high?
Okay, that's a very good question. What physics determines, the Utah is asking question, what physics determines the, soft and hard spectra?
Yeah.
So this is the direct consequence of the compression ratio of the shock, which is a result of the CME speed. So what we find, in our paper that published last year, this is exactly the question that we were trying to understand, how if we only use the particle acceleration as the particles go back and the gain energy on the shock front, using this kinetic model, to how this depends on the parameters of the shock. And we find that for the fastest CMEs, around 4,500 gallons per second to 5,000 gallons per second, we find that in order to match these fluids that we get from carbon-14 data, we need CME speed 5,000 gallons per second. Otherwise, you're not going to be able to produce so many particles.
So yeah, working on you also, but I'm working on stellar CME observations, and the velocity observation is important, right? From this point of view.
Yeah. Yeah, velocity important, but we need to keep in mind that let's say that this H alpha
Oh, yeah.
that I shown, it's only the part of the story
Yeah,
because it shows the lowest, densest, more massive part of the CME
Yeah.
structure. And looks like the simulation show, and also some of the observations show, the solar CMEs, that the H alpha velocities that we measure from blue shifts from current sun differ from the CME Fluxrod shocks by a factor of 3 to 4. So therefore, if you measure like 700 cans per second, your CMEs pretty well can be over 3,000 cans per second.
Okay, I don't see anyone raising the hands or from online. If you have any question, please ask. And if not, then let's thank our speaker again.